Alrighty, so for this lecture, we're going to continue talking about kinematics, but this time we're going to get into the main kinematics of physics. We introduced kinematics last time through the use of one-dimensional problems. So that is to say, when an object's in motion, it moves in one direction. It can move horizontally, or we could do a different problem, it moves vertically. But it's only in that one direction, up and down or left and right. We had equations, x equals v naught t plus 1/2 at squared, where remember x meant the distance, v naught meant initial velocity, t was time, a was acceleration. These were all the big variables when it came to kinematics. Next equation we had, vf squared is v naught squared plus 2ax. And then lastly we had a was vf minus vo over t, a change of velocity over time. And we found that any one-dimensional kinematics problem we had could be solved using one or multiple of these equations. And it wasn't too difficult because in these problems, the object moved either in the x direction or the y direction. However, what happens if we allow an object to move in a combination of directions? That is to say, it's allowed to move in any direction at once. How do we relate, for instance, a distance traveled when it can move a certain amount in the x direction horizontally, but a certain other amount in the y direction? What value do we put for the distance? Or, for instance, you throw a rock, for instance, let's say here's a cliff, I throw a rock horizontally. Well, intuitively we know gravity is going to affect the rock, and so the rock's going to go eventually hit the ground downwards like this. And this gives us a problem. The problem is this. The reason the rock eventually falls to the ground is because gravity acts on the rock. And as we saw in the last video, the way we handle gravity is we call it an acceleration. And we know gravity only works in the y direction, vertically. So there's one acceleration acting on this rock, and it's in the y direction. However, this rock is moving both horizontally and vertically. So if I were to try to use one of these equations, the fact that the rock can move horizontally, maybe it has a certain horizontal velocity at first, but it's got a vertical acceleration. Well, this is bad because if you remember our talk of vectors, vectors does not allow you to combine vectors, add vectors together, or anything like that if they're in different directions. So that means for these equations, because all of the variables in these equations are vectors, then in a single equation, I'm not allowed to have two different directions. When I use one of these equations, it must be completely horizontally or completely vertically. I cannot combine both directions into a single equation. So let's say I try to use the first equation, x equals v naught t plus 1/2 at squared, and I start trying to manipulate this for this example I gave. The a is going to be a y acceleration. The v naught, well, obviously when I threw the rock, I initially threw it horizontally, so the initial velocity is an x velocity. Well, this can't happen. I'm not allowed to put an x velocity, because that's an x vector, in the same equation as there's a y acceleration, because the acceleration is a y vector. That's just unallowed. So, we have to figure out then, how in the world can we solve problems where we're allowed to move in both the x and the y directions at the same time? Well, it turns out it's not as complicated as it could have been. The good news is this. while we're not allowed to do x and y in the same equations, it's also true that x stuff, all the information about the motion of the object in the x direction, is completely independent from the information of the motion in the y direction. So x and y motion is or are independent. Okay, this is good because what this means is I can look at a problem and I can break that problem, like this one, throwing a rock off a cliff, into two completely separate problems. One, thinking about the rock's motion in the x direction and using equations for x directional stuff. The other, thinking about the motion of the rock in the y direction and only using y directional stuff. And once I do those two separate individual sets of equations, maybe I combine the results at the end. But at the very least, it must be very, very clearly understood when you're going to write down an equation and start plugging information into equations, never ever plug x motion information and y motion information into the same equation. And you're going to see how I kind of help myself remember this. But if you write down an equation and you start plugging numbers in, whatever the variables are asking for, you must remember I only want the variables or the numbers for these variables in terms of a certain direction, either the x or the y. So let's remember, as an example, a problem where we have a cliff and I have a rock and I drop the rock from the top of the cliff. And let's say I happen to know that the cliff has a total height of 10 meters. And the question is, calculate the time it takes for the rock to hit the ground. Okay. Well, we did this before. First thing we can do is let's start plugging in or figuring out what is everything we know in this situation. Well, let's see. First of all, I know that the distance traveled by the rock is going to be negative 10 meters. It's going to fall 10 meters downwards. What else do I know? I dropped the rock. Well, if I dropped the rock, that means the initial velocity, as soon as it left my hand, was 0. I didn't throw it. So the initial velocity was 0. What else do I know? Well, I'm looking for the time it takes to hit the ground. And if you remember, there was one extra piece of information that's not stated in the problem, and that is the reason this rock will hit the ground is because gravity is going to pull it down. And if you remember, gravity is an acceleration in the y direction, and it's always downwards, so let's say negative 9.8. All right, this is meters, of course, meters per second squared for units. Okay, so right here I'm saying let downward be the negative direction. That's how I'm going to solve this problem. We kind of went over last time. You can do a trick where if you know everything is moving in the downward direction, then you could call the downward direction positive. But just so I don't confuse anybody, we're going to stick with the rule that downward means negative. So the motion of the rock, he falls 10, so he's negative 10 meters. The acceleration is downwards 9.8, so it's negative 9.8. All right, so once I know everything that's given in the problem and what it is I'm looking for, I could look at my equations and say, well, there's this one, x is v naught t plus 1/2 at squared. Vf squared is v naught squared plus 2ax. And acceleration is Vf minus VO over T. Those are my three equations I'm allowed to use. Now, which one can I use? Well, let's start looking at the equations. Let's start with the first equation. Can I use this equation to solve for what I want? Well, I'm looking for T. Does it have T in it? Yeah, it's got T in it, so it's allowable. The next question I have to ask is, given I'm looking for T, do I know all the other variables? So x I know it's negative 10. V naught I know is 0. A is negative 9.8, and T is what I'm looking for. So I can use that one. So let's use it. X equals V naught T plus 1/2 AT squared. All right. Now let's plug our numbers in. X, negative 10, equals V naught 0 times T plus 1/2 A, negative 9.8, times T squared. Of course, 0 times T is just 0. So now I need to solve this for T squared. If you remember, 1/2 times negative 9.8, that's just negative 4.9. So I want to solve for T squared. That means bring the negative 4.9 to the other side. So I get negative 10 over negative 4.9 equals T squared. But I don't want T squared, I want T. So I take the square root of both sides. And that gives me 1.43 seconds. And there we go. How long did it take for the rock to hit the ground? 1.4 seconds. So that's what we did last time. And you can see this is one-dimensional because the rock is only moving vertically. Well, now what I'm going to do is do a very similar problem, only now the rock is not going to purely move vertically, but it's going to move in a two-dimensional way. So here's this example. Let's take the same cliff. Here's my little cliff. Here's the rock. This time I'm going to throw the rock horizontally with an initial velocity of, let's say, 20 meters per second. Horizontally. What else do I know? The height of the cliff, again, is 10 meters. The question is, obviously, the rock is eventually going to hit the ground. I'd like to know two things. Part A, how long does it take for the rock to hit the ground? Part B, a second thing I'm allowed to ask is find the range of the rock. And what do I mean by the range? What I mean is, how far will the rock go horizontally by the time it hits the ground? That is, how far from the base of the cliff will it land? In this case, I'm showing it, let me actually do it in a different color. Let's say I want to know this distance here. So that distance is called the range. And a range generally means in physics the horizontal distance for how far an object travels. All right. So let's see, how are we going to do this? Well, let's start off the way we did before by trying to write down everything we know. Okay, now, I've already stated, so I'm going to kind of quicken the pace of discovery. I'm not going to start from the very, very basics and have you discover everything. I'm just going to say, we already know because I told you, we're going to have to look at the x direction stuff and the y direction stuff separately because they're vectors. So because of that, we already have a hint that says, when I'm looking at information, there's not just x, v naught, a, t, vf, these variables. There's those variables, but there's those variables for x and the same variables for y. So when I talk about distance x, I mean what's the distance in the x direction, but there's also what's the distance in the y direction. Okay? And v naught, the initial velocity. Well, now there's not just one initial velocity. There's an initial velocity in the x direction, but there's also an initial velocity in the y direction. So I have to be clear about how I write down the information so I understand, and people who read my work can understand, is this piece of data, is this information about the x directional motion or the y directional motion? So we just have to be careful. We can do that. Let's look at distances. So first, there's two distances in this problem. The rock can move up and down vertically, and it can also move left and right horizontally. So there's two distances. Let's look at the vertical distance. Let's call it y. What is the y distance traveled by this rock? Well, it starts at the top of the cliff, and by the time it hits the ground over here, vertically speaking, it's gone 10 meters downwards, just as before. The fact that the rock went horizontally as well makes no difference to the vertical motion. He started at the top of the cliff, he lands at the bottom of the cliff. It just so happens he's also further away. But vertically speaking, he drops 10 meters. So that's the same, minus 10. What about the x distance? How far will the rock go in the x distance? Well, I don't know. That's actually one of the things I want to know. So I'll call that x, and I'll put a question mark. That's part B. That's what I want to know, the range. All right, what about initial velocity stuff? Well, there's two initial velocities. There's initial velocity x direction, and there's initial velocity y direction. So let's look at the problem. Is there an initial velocity in the x direction? Yes. This rock is thrown horizontally with a speed of 20 meters per second. That means the x directional initial velocity is 20. So 20 meters per second for the x initial velocity. But what about the y initial velocity? Well, because I'm told that when I threw this rock, it had purely a horizontal velocity, that means there was no vertical velocity at all to its starting motion. So in essence, it's just like this previous problem where the rock was just dropped from my hand. So in the y direction, there's no initial velocity. The difference here is that while there's no y velocity initially, there was an x velocity. So again, 0 for my initial velocity in the y direction. I can come up with a different problem where there's both an x and a y initial velocity. For instance, I could say I threw the rock up at some angle. So there's some initial velocity of 20, and the angle I threw it at was 30 degrees. For that type of example, I could break that initial velocity up into something in x and something in y. But for this problem we're doing here, it's easier. Because I threw it purely horizontally, it had an x initial velocity, but the y initial velocity was 0. All right, what else? Accelerations. Let's look at accelerations. Again, there's an x acceleration and there's a y acceleration. So, do we know these? Well, again, I know this rock is going to fall down to the ground, so there's definitely a y acceleration, and that's gravity. So in the y direction, negative 9.8. So that's fine. But what about in the x? If you look at the rock moving in the x direction, is there anything making this rock speed up or slow down as it moves horizontally? Obviously, it's going to speed up as it falls, but what's speeding up is the y stuff. The y velocity gets faster and faster. But in the x direction, once it's left your hand, there's nothing pushing or pulling on that rock horizontally. So that means there's no acceleration in the x direction. Again, I could come up with a separate problem. Maybe I allow some wind to be in that problem. If there's wind in the problem, or air resistance, then yes, the air resistance will try to slow the rock down horizontally. But that's more complicated. I'm not worried about that stuff. Here, once I've thrown the rock and it's left my hand, it's just moving horizontally, willy-nilly, nothing's messing with it horizontally, so there's no acceleration horizontally. There is acceleration in vertical direction, so it speeds up downwards and falls down to the ground. But in the x direction, it doesn't. Okay, last thing, time. Of course, in time, there's no two types of time. There's time and that's it. And in this case, part A, I'm looking for the time. So this was the hardest part of the problem. The rest of the problem is going to be very easy because we've done it before. But this was the critical key piece of this problem-solving technique. You have to be very comfortable separating the x direction from the y direction. And don't allow some mistakes of thinking and intuition to combine them. You must be able to see that whatever goes on in the y direction never affects what happens in the x direction, and vice versa. A good way to think about it is this. When you have a gun, let's say you're shooting a bullet from a gun. When you shoot the gun, it goes really, really far, but eventually the bullet's going to hit the ground. It's hard to imagine, but is true, that if I were to have a bullet in my hand, and I have a gun in my other hand, I shoot the gun and drop the bullet from my other hand. Both of those bullets hit the ground at the same time. It doesn't seem like that's true. It seems like the bullet shot from the gun will go longer in the air. And the bullet that I drop from my hand will just hit the ground pretty quickly. But that's not true. It's actually been determined, and you can do experiments, and experiments have been done, where the bullet shot from a gun would hit the ground in exactly the same amount of time as if you just dropped the bullet from your hand. The fact that it's moving extremely quickly horizontally makes no difference to its vertical motion. So here the same thing applies. This rock, vertically speaking, is exactly the same as this rock from our previous example. And we're going to find out. If this is true, if what I'm saying is true, then it better be true that the time it takes for this rock to hit the ground, even though I threw it with some speed horizontally, better be exactly the same time as this rock where I just dropped it from my hand. Now, if when I do this problem here, I get a different time, then everything I just said is a bunch of BS. So let's hope I know what I'm talking about. Now that I have all my data laid out, everything in X, everything in Y, what am I looking for and what do I have, all that's finished. Now let's look at how to solve the problem. Part A. I want to know time of flight. That is, how long does it take for the object to hit the ground? I have exactly the same equations. Okay, what are those equations? Well, let me write them here. Got x equals v naught t plus 1/2 at squared. Vf squared is v naught squared plus 2ax. And acceleration is vf minus v naught over t. Same three equations. I need to solve this problem. I'm looking for a time. So which equation can I use? Well, I look at my three equations. The second equation has nothing to do with time. So I know I can't use that one. But I have the first equation, and I have the third equation, has t in it. Okay, well, can I use the first equation? Here's where things differ for the second time. The first difference came when we're writing all our data down. We have to worry about X stuff and Y stuff separately. Now the new difference is, now that I'm looking at the equations, which equations I'm allowed to use, I have to remember when I ask these questions, I'm only looking in X or I'm only looking in Y. So let's try it. Let's look at the first equation. There's a t. I'm looking for a t. That's good. Do I have all the information? Well, let's look in the x direction first. In the x direction, I need to know the acceleration. I do know x acceleration is 0, okay? I need to know initial velocity in the x direction. I know initial velocity in the x direction, that's 20. I need to know the x distance. I don't know the x distance. Uh-oh, I'm stuck. Don't be fooled by thinking, well, I do know the y distance, so why don't I just put the y distance there? And then I have all the information. I have a y distance, x velocity, x acceleration. You can't do it. Again, this is a vector equation. And vectors, every equation with a vector, everything must be the same direction. So if I'm looking at x, it's all x. If I'm looking at y, it's all y. So I know I cannot use the first equation in the x direction. The reason is because while I have everything I need, I don't have the x. I don't have the distance in the x direction. So I'm missing something. However, now I can ask the same question about the y direction. Do I know all the information in the y direction instead? Well, again, I'm looking for t. Acceleration, do I know the acceleration in y? That's negative 9.8. Do I know the initial velocity in y? That's 0. Do I know the distance in y? Negative 10. Aha. Now I have all the information I need. Be very careful. Just because I wrote here x, that doesn't mean x direction. Okay? That variable is just a variable name which means distance. So that distance can mean x distance or y distance. And what you'll find in a physics textbook, especially a beginner's physics textbook, is when they write these 3 equations down that are in yellow, they'll write 6 equations, or actually 8, because I'm not showing you a 4th equation that you never need. They'll write these 3 for x, and then they'll write the same 3 all over again, but there's y's everywhere. Because they think your mind isn't big enough and you're not old enough to be able to distinguish between an x distance and a y distance unless you physically see y sitting there. But we're in college, we're adults, we have the ability to say, look, I know this equation means distance. It doesn't mean x distance. Distance allows us to either think x or y. Okay, so just be very careful about that, especially if this is your first time going through this stuff. Don't think that everywhere I have an x written here, I literally mean x distance. All I mean is it's a variable name. I could write a D, I could write L, I could write H. The Germans write S. I can write any variable letter. All the letter means is it means distance. And it's up to you to apply, do I mean the distance in the x direction or the y direction? Okay, just wanted to be clear about that. So, I've gone through my little questioning. I know I'm going to use the first equation. I saw I couldn't use it in the x direction because I don't know the distance in x. But I could use the first equation in the y direction because I know all the information about y. So that's what I'm going to do. Now, when I do it, especially when I know someone's going to read my work, I put this little y. And that says the equation I'm about to use is going to be used for the y direction. Okay? If I were to do this equation in the x direction, then I'll put a little x with an underline, just to let everybody know the equation you're about to see is using y directional data or x directional data. Don't think that I'm dividing y by something or anything like that. This is just so when someone reads my work, they can see at a glance the equation that's about to come will use y information. All right, so here we go. X equals v naught t plus 1/2 at squared. That's my equation. Again, y directional stuff only. So let's plug my information in. What's the distance in the y direction? -10. V naught, that is y v naught. The y v naught is 0 times t, but 0 times t is the same as 0, so I don't have to write t, plus 1/2. The acceleration, again, it's a y acceleration, which in this case is -9.8 times t squared. So again, I want to solve this for t. I divide this 1/2 of -9.8 over, and I get -10 over -4.9 equals t squared. I don't like t squared, so I take the square root of both sides, and I get square root of this is 1.43. And what do you know? Here, the time it takes for this rock to hit the ground is exactly the same as it was before, even though in our new example, I've given this rock an initial velocity in the horizontal direction. So this goes to show that the fact that the rock had some horizontal motion initially makes no difference to its vertical motion. The rock's going to fall down and hit the ground at exactly the same amount of time, whether I threw the rock at 100 meters per second or I just dropped it from my hand. Now, of course, if I threw the rock vertically, obviously that's going to change how long it takes, because if I threw it down, straight down to the ground, then it starts with an initial velocity in the vertical direction, so of course it's going to hit the ground faster. If I threw the rock up initially, then it's going to take longer to hit the ground because it goes up first and then it's going to come back down. But in this case, the initial motion of my rock was horizontal, but the equation I used was a vertical equation. So of course, none of the horizontal motion comes into play when I'm using a vertical equation. All right, well, what about part B? Find the range of the rock. What do I do for this? So B, find the range. Well, I'm going to do exactly the same thing. I'm going to look at the equations I'm given, and I'm going to ask myself which equations allow me to do this. Well, in order to do this, I need to understand what does it mean to find the range of the rock. And I already said it before. What it means is how far will the rock go horizontally by the time it hits the ground. So what's this horizontal distance from here to here? Okay, well, I already know I don't care about y-directional stuff anymore. I'm looking for an x distance. So no matter which equation I'm about to use, it must be in the x direction. So I don't even have to worry about y stuff. All I'm going to look at is, for these three equations, which one allows me to use x directional information to get the distance. All right, let's look at the equations. I've got three equations. The third equation, A is VF minus VO over T, doesn't have an x in it, doesn't have distance. So I know I'm not going to use that equation. So it must be one of the first two. What about the second equation? Can I use the second equation? Well, I'm looking for x. It does have x. Good. Do I have the x acceleration? Yep, it's 0. Do I have the x initial velocity? Yep, it's 20. Do I have the x final velocity? Well, technically, I do know the final velocity in the x direction, even though I didn't write it. And the reason I know is because since there's no acceleration in the x direction, that must mean the final velocity is the same as the initial velocity. There's no difference. It's not speeding up or slowing down. But if I were to try using this equation, I'm just going to tell you right now, everything's going to turn out to be 0. You can try it. You can write down the information, and you'll find out you get a 0. So it doesn't matter. What about the first equation? And by the way, I'll just prove it to you, just so it's clear. Say I want to use this equation. Vf squared is v naught squared plus 2ax. Right? That's what I want to use. I'm looking for x. That's what I want. So plugging my numbers in, Vf squared, since I know acceleration in x is 0, it must be true that my final velocity is the same as the initial velocity because it didn't change. So this must be 20. Initial velocity I know is 20 plus 2 times acceleration is 0 in x direction times x. But this is bad. Look. X is being multiplied by 0, so this term goes away. So now my equation doesn't even have an x in it. So I know, oh, there's something wrong. This equation isn't going to work. I may as well erase it. So get rid of the equation and go to the other one. Now I know it must be the first equation. Okay? So if this happens on a test, it's no big deal. All it means is that equation shouldn't have been used. So just erase it and go to the other equation. Yeah, you may have wasted a little time, but that's not a big deal. Look at the first equation. Can I use it? Again, I'm looking in the x direction only. I have an x. X is what I want, so that's good. V naught in the x direction, yep, it's 20. T, do I know the time? Well, I didn't before, but part A just told me what the time is. So I do know the time. Do I know the acceleration in the x direction? It's 0. And again, time. I know the time. So I'm allowed to use the first equation. So x equals v naught t plus 1/2 a t squared. And now I plug my numbers in. V naught, what's the x directional initial velocity? 20. What's the time? 1.43. Plus 1/2. Acceleration in x is 0 times t, but I don't need to write it because it's all multiplied by 0, but I'll write it anyway. And if you remember, let me go ahead and write it just so everybody knows I'm looking in the x direction here. So there we go. This term is 0, and so it's just 20 times 1.43, and I get x equals 28.6. So how far will the rock travel horizontally by the time it hits the ground? 28 meters. So you see, our previous example, which was one-dimensional kinematics, what was the process? Listen to the problem. Maybe I sketched the little problem so I could get a visual idea of what's going on. I write down all the information given in the problem, as well as what it is I'm looking for. I have the equations I'm allowed to use, and then I start asking myself questions. If I'm looking for time, which equation can I use to calculate time? And I go through, I look at the first one. Does it have a t? If it does have a t, do I have all the other information? If I don't, I move on to the next equation. If I do, then I use the equation. I use the equation, plug all the numbers in, solve for whatever variable I'm looking for algebraically, and I get my answer. Here we have a two-dimensional problem, but the method is the same. First step, listen to the problem, sketch out the problem if you have to, if it's not already done for you. Write down all the information given in a problem. Now, to me, the best way to do it is to separate it into x and y stuff specifically. Show it when you're writing down the information so it's not confusing. Here's my x distance, here's my y distance. Here's my x initial velocity, here's my y initial velocity. Here's my x acceleration, and so on. We write it all down, as well as what are the things we're looking for. Then, what is the first thing we're looking for? All right, now, which equations do I have? Same exact equations. They don't change. Whatever equations I was using before, they're the same ones now. So I go through the same process. The only difference now is when I ask myself questions about using the equation, I have to do it twice. I do it once in the x direction and once in the y direction. If you remember, for part A, finding the time it takes to hit the ground, I said, can I use the first equation? I can because there's a t in the equation. Then I said, okay, I have two options. I can either use the equation with x information or I could use it with y information. So let's see if I could use x stuff. So, okay, well, I know a in the x direction, that was 0. I know v naught in the x direction, that was 20. But the x in the x direction, I don't know. So it fails. However, I've got my second option. Redo the same questions, but now say y direction stuff. Do I know the a in the y direction? Negative 9.8. Do I know the v naught in the y direction? That's 0. Do I know the distance x in the y direction? Negative 10. Aha! Now I can use the first equation, but I know I can only use it for y direction information. So I write, I'm looking in the y direction. Here's my equation. Plug the numbers into the equation and solve for the variable. And there you go. Same exact thing, only I just have to be careful when I plug my numbers in to only use x or only use y. Part B, same thing happens. What is it I'm looking for? I'm looking for the range. What does range mean? Range means horizontal distance. Well, that's good. That automatically tells me I have to look in the x direction. So don't even ask about the y direction because it doesn't matter. So I'm looking for range. I'm going to use x direction. That's what that means there. Then I go through my equations just like before. Can I use the first equation? I'm looking for distance. First equation has distance in it. That's good. What about the rest of the information? Do I have that stuff? Do I have v naught in the x direction? 20. Good. Do I have t? At first I didn't have it, but part A gave me time. So yes, I do have the time. And remember, even though I solve for time in the y direction, that doesn't mean somehow this time is a y directional thing. Time is special because it doesn't have a direction associated with it. Time is just time. So you can use time in x or y, it doesn't matter. All right, what about A? A in the x direction I know is 0. Okay, so I can use the first equation because I'm looking for x, and there's an x in it, and I have all the information I need in the x direction. So I plug my numbers in, solve for the variable I need, and I get my answer, just as before. So I hope this makes sense. Yes, it's a little more tedious because there's more things to keep track of. But if you're organized and you write down everything separately, x stuff separate from y stuff, and you label it for yourself, then you don't really have to keep track of it because you've already done it by writing it all down. When you ask questions, you just look at your list of information and you either say yes or no. I know it or I don't know it. If you know it, plug the stuff into the equation. If you don't know it, move on to the next thing. All right, so that's pretty much it for this. The main takeaway is now that things move in two separate directions, or any direction they want, everything given in the problem has to be done x and y separately. Okay, I'm going to do a follow-up video with some examples. One of the examples is going to be something where, here's the ground, and there's a cannon, and a cannon shoots a cannonball at an angle. So maybe 30 degrees with an initial velocity of 20. And I want to know how far will the cannonball go, or how high will it go, things like this. Well, we have to do the same kind of technique we did here, except here the initial velocity was already broken into x direction stuff for you. For this problem, it's not. This velocity is at an angle. But that's not a big deal because we spent some time at the beginning of the semester with trigonometry specifically for this. Because this velocity is at an angle, and I know angles are bad for vectors, the very first step I'm going to do is break up into this velocity into its components. So it's going to be some amount of velocity in x, some amount in y. And of course, you're going to find is 20 cosine 30 and 20 sine 30. Exactly what we did with vectors and trigonometry before. Now you see where it's going to come into play. This velocity is at an angle, but I know when I solve my problems, I can't have angles. It must either be x or y. So before I can do any of my equation stuff, in order to list this data on the left, I have to first take this angled piece of information and break it up into an x piece and a y piece, which we saw how to do before. Once I do that, then I know this is 10 and this is 17.32, I believe. Then I know V naught x is 17.32, V naught y is 10. No big deal. Just like here, V naught x is 20 and V naught y is 0. There they are. How I got them doesn't matter as long as I got them. So the next lecture, or video I should say, is going to have some examples taking this kind of stuff into account. So it's going to be slightly more complicated questions. But they're only more complicated in the fact that you have to do this calculation before anything else. Once you've done this calculation, the problem is exactly the same as this problem. No difference whatsoever, which is very nice. Once you know how to use these three equations in yellow, and you know how to take information that's at an angle and put them into x and y pieces, which we did at the beginning of the semester, then all of these problems will fall into place. So, hope this makes sense. Again, as always, if you have questions, feel free to email me. But be on the lookout for the next video with examples on this, as well as some practice problems I'll be posting on Canvas as well. Until next time.